Welcome back, and we are doing the discussion the basics of the turbulent reacting system, what you need and what are the governing equations, and then we will continue the discussion. So, this is where we start looking at all the set of equations that one need, like all these transport equations, transport properties, kinetics, thermodynamics, state, and this that will get you continuity, Navier-Stokes, species, and this. Now, there is a statistical approach description for the turbulence. This is already we have discussed in details, because this is one of the issues in modeling. When you look at the RANS, which is very simple to use, but only solve for the mean values, whether LES solve for large scale structure, it models the small scale structure, and when you look at DNS, it solve all details. Now, when you looked at the only turbulent system, that time we didn't need to bother about the reaction and other things which are quite critical under reacting system. So, one of the issues which one may find is the closure problem of this chemical source term in both in RANS and LES. As long as we are doing DNS, we resolve all the scale and we solve without any closure or any other assumption, but when you come to LES or RANS, we need some closure thing. This is typically how an signal is represented, because if you have a fluctuating component which can be obtained from the instantaneous component minus the mean value. So, when you go to some of the issues that we will touch upon here, then when you go into the details of those particular discussion like premix flame and something, then we will see how that impacts. Now, one of the issue which will people find in LES of the premix flame, see LES has an grid size like this, or rather the filter size which is of order of delta. Now, laminar flame thickness or the flame thickness of the premix flame quite small or very small. So, what happens, essentially the flame front sit inside an grid cell. So, which means the filter size or the grid size is quite larger than the thickness. So, that allows a different challenge to how to resolve this flame front. So, this is what this is quite small than the Kolmogorov scale and the filter size is larger. So, one need to be careful to handle that kind of situation, because the flame front may sit inside the grid cell. Then another thing what will come is the flame front. This is our flame front or wrinkled flame front, this is the flame surface. So, the burning velocity. So, as long as we are dealing with the laminar laminar flame, the only thing that we are concerned about the laminar speed. But when you talk about the turbulent system, then there is a burning velocity, you get in component which is known as turbulent flame speed. So, for DNS, the speed of propagation of the instantaneous isocontour, which is relative to the reactants. So, that is what the speed of the flame front. RANS, the speed of propagation of the flame branch relative to the main reactant, this is what you get in the laminar, that is the turbulent burning velocity, and LES also it is to the resolved. Now, in RANS and LES, this is an issue how we get the closure for the turbulent flame speed, because that requires some calculation. Now, typically in RANS, it is usually expressed via some correlations. Now, if your grid tends to 0, then this becomes grid independent, and also for LES part of the subgrid model, this should be approaching towards the flame speed that you get in the DNS. So, but a good model should allow to compute the turbulent flame speed. So, if we put these things, that there are different methods for analysis of this turbulence flame. Now, method, depending on the method, also RANS or LES things would change. Now, one option is that this is typically a flame front and this is the normal across the flame front. So, one approach is that is the isosurface analysis, which actually study the topology and dynamics of the iso-level surface. In premix flame, this iso-surface is called progress variable, and the non-premix case is the iso-mixture fraction. Now, the second approach is flame normal analysis. There you gather the information in the direction normal to the flame surface and do the analysis, or you can have some point analysis which collect information at every point and do the analysis, or edge flame analysis. Now, flamelet model or PDF models are respectively based on flame normal analysis and 1 point. So, when you look at the flame normal analysis, that means you try to derive your system or convert the system along the flame normal directions. So, that is where you get flamelet kind of model. That means you try to define your turbulent flame front to be ensemble of small laminar flame brush, or when you try to collect based on point analysis, this is where you get the PDF kind of approach, which we have seen in the turbulent case. Now, that means if you have flame normal analysis, that will lead to flamelet model. So, which means the structure normal to the flame surface in turbulent flame is assumed to be the same as the laminar flame. So, probability density function of the independent variable C or Z is used, or if you use 1 point analysis, that will lead to PDF kind of methods, where the equation of probability density function fluctuation at 1 point are modeled and solved. Now, the success accuracy of these kind of models depend on the type of flame, whether it is premix, non-premix, partially premix. But one important thing which will come into the picture is the Damcoulon number, which is the ratio of two time scale between your flow and kinetics. So, complete the model, we have transport equation, which is mass, momentum, species, energy or temperature plus transport properties, kinetics and other things like thermodynamics equation of state, caloric equation of state, radiative transfer equation, radiative properties, etc. So, we can start with the continuity equation, and that is one can write del rho by del T dot rho V equals to 0, which will get us d rho by dt equals to minus rho del dot V. So, here like an incompressible case, the d rho by dt is not 0, because this is a reacting system. Due to temperature, the variation of density is there. So, one has to solve this variable density situation. Now, if you have multi component fluid, which typically happens or present in the system, you need to get the system density to be sum of these different species. For example, if you consider air has by and large oxygen, nitrogen, but then you can have H2, some amount of H2O, some amount of CO, CO2 and so on, but this may be by volume very less, but there are multiple species. When you have multiple species, the summation of that density would give you the total density. So, like we can have the system density, it will satisfy the continuity equation, but what about this term? Now, at the total density or the mixture density, that satisfied the continuity, but what happens to individual term? We will see how this leads to our individual species mass transfer equation. Now, as I said that you can have the multiple species in a system, and then they could have different proportion. One way to represent that is by mass fraction, another option is that mole fraction, that we have seen, and typically we use this is the representation for the mole fraction, and this would be for the mass fraction. So, just to recap these things, you have molar mass Wi, then mass density, and mass fraction would be rho I by rho. This is how, and the total mass of the system should be 1. Similarly, molar density, you have a mole fraction, and summation of mole fraction also should be 1. Now, you can have mean molar mass W, which is summation of I equals to 1 to n xi Wi, then y by W is summation of yj 1 by Wj. So, we can have conversion from one to other, yi equals to Wi by W bar xi, which is xi Wi by summation of j, and xi is W bar by Wi yi, which is yi by Wi divided by yj by Wj. So, one can represent sometimes the mass fraction and sometimes the. So, this is another important thing, that mass based mixture velocity and the diffusion velocity. So, the species velocity is Vi, which is acting in this direction, and the mixture velocity, which is summation of yi and Vi, which will be acting on this. So, the diffusion velocity is the difference between these two velocity. So, the species which are there in the system, that summation yi 1, and if we take the product of yi by Vi, that should be 0. So, that means in a momentum balance for the total mixture, a mass weighted average velocity is needed. This is an important point to be noted here, that mass weighted. Now, we have species mass flux, which is rho I Vi, then the also due to the reaction there would be species production rate or destruction rate. So, that is omega dot I. Then for this small control volume, one can get the species mass conservation. So, which in turn get you del rho I by del T. So, this is your species mass conservation equation and individual So, if I expand this term of the mass flux, this is rho I V I, rho I V plus V I, then this is the relative mass flux term, which is nothing but rho I and the diffusion velocity. So, if I put these things here in the equation of the species mass conservation, and what we get, that this is the convection, this is convection with the diffusion velocity, and this is now this particular term, there are different models for this diffusion flux. There is Fick's model, Wilkes model, Stefan Maxwell's model, general multi-component diffusion. So, there are different ways one can represent these models for this. Now, that is why if you use Fick's law of diffusion, so if you take a case of binary system with two species A and B, then my rho I plus del dot rho I V bar equals to minus del dot rho I V I plus omega dot I. Here I equals to 1 and 2, which is rather A and B. So, rho A would be rho into Y A. So, that means J A is rho A V A minus rho A, and from here what we get, del del T for rho Y A dot rho Y A V bar dot rho D A B plus omega A. So, this is an mass fraction equation for species A, provided density, mixture velocity, diffusion constant, all these are known. Now, we can use the Fick's law for multi-component diffusion. So, we can select one carrier gas, for example, let us say we take nitrogen, then we solve the species transport equation with diffusion velocity equals to din del I, where I equals to 1 to n minus 1, and this is nothing but binary diffusion coefficient. So, then we can solve for the carrier species, that is number 1. Step 2, we can solve for the carrier species, which is 1 minus summation of to 1 minus 1 y I. So, which guarantees that summation of y I p I bar is 0. So, that is how similarly we can use the Wilkes model for multi-component diffusion, where again we have to select an carrier gas, let us say nitrogen. Then step 1 we solve for the transport equation with Wilke dim bar, where I equals to 1 to n minus 1. Here this guy is the composition dependent diffusion coefficient. Secondly, we solve for the carrier species, which is 1 minus summation of I y I, and that guarantees y I equals to 0 for I goes to 1 to n. So, we can see some example where the temperature and the steam function in a premix laminar flame impinging on a surface. This is an methane air flame with 25 reactions, 16 species. This is acetylene oxalate flame with so many reactions. So, depending on the situation, the flame shape and all these things changes. Now, momentum transport, you get rho dot sigma plus rho f, where sigma is the stress tensor which has P plus 2/3 mu del dot V I plus mu del V plus V. Now, body forces, if you have a is summation of yk fk. Now, we can have some internal energy, total energy and enthalpy for, let us say, we consider mass m, then specific internal energy U would be U by m, where internal energy U can be used as du equals to del q minus p dv, which you get from the first law of thermodynamics, and this is U plus half m, and total enthalpy is U plus PV, where dH equals to del Q plus V dP. Here Q is the heat added to the system. So, this is the per unit mass. So, specific total energy per unit mass would be E plus half V, specific enthalpy would be E plus P by rho, or Et minus half P by rho. So, these are some of the terminologies which will be required. Now, different possibilities to describe the conservation of energy. So, the either one can do that in terms of specific total energy, which is most suitable in studies where compressive effects are important, or specific internal energy or specific enthalpy. This is also study, I mean the specific enthalpy is quite often used or most suitable for this kind of combustion process, or the temperature. These are suitably used in incompressible situation where the density variation is not there due to change. This is what already we have talked about from the connectivity between internal energy and enthalpy and all this. So, now if you look at the conservation of the total energy, so the energy flux, there would be two components, one is the convective flux, another is the diffusive flux. So, this is the component coming from the convective flux and this is the component due to diffusion flux. So, if we write down in terms of the volume integral, this is what we get. There is the unsteady term, convection, diffusion and source term of the energy. So, we can see the individual term like this Q, you can have Q conduction, you can have interdiffusion, or you can have effect of Dufour. So, we use the Fourier's law of heat conduction, where this can be represented as lambda del T, this is represented as rho summation of I equals to 1 to n Hi, Yi, Vi, and the Dufour effect is defined as RUT summation of I equals to 1 to n summation of j equals to 1 to n xj alpha j Wy dij Vi minus Vj, where alpha j is thermal diffusivity. So, this conduction contributes due to the thermal gradient. Interdiffusion is due to the species diffusion, and the Dufour effect, this is the heat flux due to gradient in species concentration. So, this is an counterpart of Sauret effect, which is also mostly negligible. This is flux due to pressure gradient. Now, we can see the similarity between transport laws. So, we have mass where J is minus dAb rho a, this is from Fick's law. Then Jy is minus del Gm by del y of rho j, this is what we got from Wilkes. Momentum, this is mass diffusion. Momentum, we have tau yx equals to nu del y by rho Vx. Heat, we have Fourier, where Qy equals to minus alpha del y of rho Cpt. So, nu is mu by rho, alpha is lambda by rho Cp. So, the some dimensionless parameter which are quite important is that Smith number, it's nu by dJm, then Prandtl number which is nu by alpha, and Lewis number which is alpha by dJm. So, these are the non-dimensional parameter which, so there is a similarity or rather the connectivity between different law. So, the Smith number which connects mass diffusion to the momentum, Prandtl number is a mass diffusion to or a momentum to thermal, Lewis number mass to thermal. So, these are the non-dimensional parameter then one need to know. So, we will stop here today and continue this discussion in the subsequent lecture.